Today we are going to finish up section 4.2. To the bottom of the Unit 2 module, there's something that says 4.2 exercises. Hold on, I'm trying to make sure I didn't miss anything. Yes, 4.2 exercises. And we're going to look at these 2 word problems. And after these 2 word problems, then we'll go to the 4.2 day 2 lab, and that'll be it for today. I did not leave myself enough space here to work out the whole problem, but we'll get it done. All right. So when we think about, because we're almost done with this chapter, we really only have like 2 more sections after this. You'll see a lot of problems that look very similar. So remember, in chapter 3, we had matrices, and then we had these word problems where we could set up systems of equations based on the word problems. And then we can use matrices and reduce the matrix to solve the system of equations. Now, with these word problems, we'll have systems of inequalities, okay? And basically, how do we know whether or not we have an equation versus an inequality? The problems will look very, very similar. There are very subtle differences in the wording to let you know whether you have an inequality or an equal sign. The words we want to look for. Keywords such as, if you read this first problem, it says a diet is to contain at least 16 units of carbohydrates and 20 units of protein. And then we're given all of this other information, okay? And then we're asked to find the minimum cost, okay? So when you see key phrases like at least or at most, that means we don't have to have exactly 16 units of carbohydrates. We can have 16 units, or we can have more than that, but it has to be at least. So that gives us an inequality instead of an equal sign. If the problem said instead, a diet is to have 16 carbohydrates, exactly that amount, then when we set up our equation, it should be for carbohydrates, it should be equal to 16. In this case, since we're given that the diet has to have at least 16 carbohydrates, we're fine with 16 or anything greater than that. So when you have key phrases like at least or at most, we want to look for those. That's how we know we have inequalities. All right, that's the first thing. So when we read this, we're going to try to figure out what our objective function is, set up a system of inequalities for our constraints, and then from there, graph to find our corner points and solve the problem. All right, let's read it. How do I get this to go away? I guess it won't. All right, so exercise 1. A diet is to contain at least 16 units of carbohydrates and 20 units of protein, okay? Food A contains 2 units of carbohydrates and 4 units of protein. Food B contains 2 units of carbohydrates and 1 unit of protein. If food A costs $1.20 per unit and food B costs 80 cents per unit, how many units of each food should be purchased in order to minimize the cost, and what is the minimum cost? So when you do these problems, please read the entire problem. Once you get to the question, that helps us figure out what our unknown should be, like what is X and what is Y in this situation, and also what our objective function is, what we're trying to maximize. Our question is, how many units of each food should be purchased in order to minimize the cost, and what is the minimum cost? So in this case, what is our objective? We want to minimize the cost function. And how are we minimizing the cost function? By figuring out, what are we buying? Let me start there. We have to buy each type of food. Here we have 2 different types of food A and food B. And we want to know how many units of each type of food we should buy, okay? So we're trying to find the number of units of each type of food. Each of those things should be labeled with a variable. So we can say, let X represent the number of units of food A. And we can let Y represent the number of units of food B. Okay? You should always start off there. If you're using X's and Y's or A's and B's or Z's, whatever variables you have, you need to tell me what those variables represent. So identify and label your variables. All right, those are the things we're trying to find. How many units of A and B we should purchase in order to minimize the cost. And then we also want to list out our objective function. All right, so our objective function here, we want to minimize C, the cost. And what do we know about the cost? We are told that food A is $1.20 per unit and food B is 80 cents per unit. So if X is the units of food A and Y is the units of food B, putting all of this together, we get that the cost function is $1.20 times X. So that's $1.20 times the units of food A that we're buying, plus 80 cents, so 0.80 times Y. This is our cost function. All right, I'll pause here for a bit. Again, you want to read the entire problem. And at first, looking at these problems, it seems like a lot, but it's really just about organizing your data and breaking it down to the question. What am I being asked for? Once you get to the question, you should be able to figure out what your unknowns are. We're being asked how many units of each food we should buy. Okay, so we don't know that yet. We need to assign variables to the number of units of each food, okay? You'll always have in these types of problems, maximize or minimize something. Whatever you're maximizing or minimizing, that is your objective function. And you should be given information in the problem to write out that objective function. So here we were told the cost of each food, food A and food B. All right, now for the fun part, the constraints. Let's color code some stuff. So in this problem, we are told, I already used purple and red, so I have to use blue and green. All right, let's go with green. We're told we want at least 16 units of carbohydrates and at least 20 units of protein. How are we gonna get these carbohydrates and protein from food A and food B? Let's look at the carbohydrates. Food A contains 2 units of carbohydrates and food B contains 2 units of carbohydrates. For the protein, food A contains 4 units of protein and food B contains 1 unit of protein. So the idea here is we have constraints on or limits basically, on the amount of carbs and protein that we need. We know we need at least 16 grams of carbs and at least 20 grams of protein. This is where we get our constraints, which are our inequalities. Okay, so constraints. We should have an inequality for each of the constraints. The first one is going to be on carbs. I can write a little neater than that. And the second constraint is for the protein. And we want to write out inequalities to represent how many carbs and how much protein we can have based on the information that's given here. So starting with the carbs, we're going to use the green underlined information. I'll put a little green star here so we know what information we used. For food A, we get 2 units of carbohydrates, okay? So 2 times X, okay? For every unit of food A, we get 2 units of carbohydrates. And then for food B, it's also 2 units, so plus 2 times Y. When we add these two together, it says that we need at least 16 units of carbohydrates. Now this is where it gets interesting. We need an inequality symbol there. Do we have a greater than or equal to or less than or equal to? At least means 16 is the smallest amount of carbohydrates we can have. We can have more than that also though. So this would be greater than or equal to 16. 2x plus 2y is greater than or equal to 16. Similarly, for the protein, if we look at our blue underlined information, for food A, we get 4 units of protein, so that would be 4x. For food B, we get 1 unit of protein, so just 1y or y. When we add those together, we need at least 20 units of protein. So that should be greater than or equal to 20. Okay. And then it's not stated here explicitly, but in this case where we have an actual application problem, X and Y are the number of units of food. We can't have a negative number of units of food, right? So X and Y have to be greater than 0. X is greater than 0. Y is greater than 0. In our application problems, that's generally the case. All right, now we have taken this word problem and set up a linear programming problem like we saw in the last class. We have our objective function, C, and we have our constraints. 2x plus 2y is greater than or equal to 16. 4x plus y is greater than or equal to 20. Any questions about this part? Now keep in mind, you guys, for not just this section, for this section and section 4.3, 4.4, 4.5, the rest of the sections that we're going to look at in class, pretty much all of our problems going forward, we're going to have word problems like this. And the biggest part of your battle is going to be setting up your word problem correctly. So we'll do a lot of practice with this. You will have to be able to do this on your own. A lot. Take the word problem, and from the word problem, find your objective function and find your constraints. Some of you may find it helpful, like I like to underline and color coordinate. Some of you may find it helpful to instead make a table of data. So you can say, oh, for food A, and then food B, and then we have carbs and protein. This is another way you can organize your data. Take the information that's given. Food A had 2 units of carbs and 4 units of protein. Food B had 2 and 1. Organize that data in a table like this, and then it'll make it easier for you to write out your your constraints. So this is just a setup. Now we actually have to solve this. So we're going to have to graph those, take those inequalities, graph the lines we get from them, find the corner points, plug them into the objective function, all that fun stuff. All right. Now, because of the way that I made this PDF, I didn't leave myself enough space. So I am going to scroll down and just draw it at the bottom. I'll have to erase. So I'll rewrite this problem down here so we can sketch it. We have 2x plus 2y. We'll want to look at that equals 16, and 4x plus y equals 20. So these are the equations we get from our 2 inequalities. I usually color coordinate this. We want to find the x-intercept and the y-intercept. For the first one, the x-intercept, give myself more room. We'd have a 2x plus 2 times 0 equals 16. 2x equals 16, x equals 8. So 8 comma 0. And for the y-intercept, it'll also be 8. 2 times 0 plus 2 times y equals 16. 2y equals 16, so y equals 8. 0 comma 8. For our next line, the x-intercept would be 4x plus 0 equals 20. 4x equals 20, so x equals 5. That's 5 comma 0. And for the y-intercept, 4x plus 4 times 0 plus y equals 20. Y equals 20, so 0 comma 20 is our y-intercept. We then want to, I didn't give myself enough space at all, but it's okay. We can do this. We're gonna sketch these 2 lines, find the corner points, and plug the corner points into the objective function, and then finally answer the question. Let's see. Ew, that's ugly. Okay, let's try this again. There we go. We know that X and Y are both greater than 0, so we're just going to look at the first quadrant. Boom. Boom. That's going to have to be big enough for today. All right. Label your axes. That's the y-axis. This is the x-axis. And I'll let these little tick marks go by 2s because we need to go up to y is 20. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, and then we can just do tick marks of 1 on the x-axis. It doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's enough. All right. Now, I'm going to pause really quickly here. Remember, when we have a problem like this where you're trying to solve this graphically, your graph is part of your actual solution in your work. So you do want to make sure that your graph is neat and labeled properly. Your scale should be clear. So that's why I'm writing, like, what do my tick marks represent here? I should be able to see your shaded feasible region. I should be able to see your corner points. Do remember that when I grade this problem, the graph is going to be a part of the grade as well. All right, let's plot stuff. So 0, 8 is down, 8, 0 is down here. 0, 8 is here. And then if I connect those two, boom, there's one of our lines. The next, for the blue one, we have 5, 0. And what's the other one? 0, 20, all the way up here. And if we connect those, boom. All right, so here is our graph of our 2 lines. We want to pick a test point. Oh, I can't erase that. All right, we want to pick a test point and determine which side of the line should we shade in. Should we shade in everything under these lines or everything above these lines? Remember, both of our inequalities were greater than or equal to, okay? So we have 2 times 0 plus 2 times 0 is greater than or equal to 16. That's false. And 4 times 0 plus 0 is greater than or equal to 20. That's also false. What does this mean? So our test point was here. We want to shade in everything that's on the opposite side of both of these lines. So I draw my little arrows like this. We want everything above the red line and above the blue line. When it comes to this shading, if you look at the way the red and blue lines cross, it kind of breaks the first quadrant into 4 different pieces. We want to know which one of these pieces works for both of the lines. And if you see, obviously, I call this one section 1. Section 1 is below both of the lines. It doesn't work. Section 2 here, this is above the red line, but it's below the blue line, so it wouldn't work. Section 3 is above the blue line, but it's below the red line, so it wouldn't work. And then this last section, the biggest section, which is unbounded, it's above both lines. It's the best I can shade for today, y'all. So our feasible solution region would be this region. It keeps going on and on upward, but that's okay because we want to, it doesn't matter that it keeps going on and on because we're trying to minimize in this function anyway. That's our objective, to find the minimum. All righty, so almost done with the first problem, y'all. All right, so we've done all of this. Now we need to find our corner points. Let's see. I usually make my corner points purple, so let's stick with that. The corner points of this region would be this one, oops, wrong one, this one, and the intersection here of the 2 points, which looks like it's at 4, 4, but we're gonna have to double check to make sure that that is true. All right. Okay, again, I've run out of space here. So I'm gonna go to the Zoom whiteboard to finish up the problem and find that intersection point. So from here, what we need to do is label our corner points. One is 0, 20, one is 8, 0, and then we need to find the intersection of these two lines to find the third corner point. And once we have those corner points, we'll plug them into our objective function to find the maximum or minimum. All right, so our lines were 2x plus 2y equals 16, and then 4x plus y equals 20. We want to know when these two lines are equal. If we solve this first one for y, this would be 2y equals negative 2x plus 16, y equals negative x plus 8. And then for the second one, y is equal to negative 4x plus 20. So setting these equal to each other, negative x plus 8 equals negative 4x plus 20. All right, so then we'd have add 4x to both sides. That would give us 3x. And if we subtract 8 from both sides, that would give us 12. 3x equals 12. And x equals 4. Then to find y, you can plug x into either of the original two equations. Y would be equal to negative 4 plus 8, which is 4. So this gives us a corner point of 4, 4. All right, last part. Our corner points. We had on the graph 0, 20, 8, 0, and then this intersection point 4, 4. And then our objective function that we're trying to minimize was the cost. C equals 1.20x plus 0.80y. All right, let's plug these in. So for the first one, 0, 20, that'll be 1.20, 0 plus 0.80 times 20. And 0.8 times 20 is 16. For the next one, we have C equals 120 times 8 plus 0.80 times 0. 120 times 8 is 9.6. And for the last one, 4 times 120 plus 0.8 times 4. Sorry, I wrote it backwards for the other one, but that's okay. 120 times 4 is 4.8. And then 0.8 times 4 is 3.2. Adding those together, we get 8. So our goal was to minimize the cost function. When we look at this, we see the minimum cost occurs here when x and y are 4. So writing this up in a sentence, remember in this problem what the 4 and the 4 represent. So we don't want to just say when x equals 4 and y equals 4. Remember, x represented the number of units of food A. If you go back to the beginning of the problem, y is the number of units of food B. So we can say when 4 units of A and 4 units of B are purchased, we get a minimum cost of $8. And that would be our final answer. We made it through one. I love these problems. It's like a lot of pieces. You guys have to take our time and put them together. But the key here is you do need to take your time. After you do enough of these, you'll, like, once you do your homework assignment, you'll notice the patterns. You can probably move them a little bit quicker than I do in class. But it should take you usually about 15 or 20 minutes maybe to do these. Some people might finish in like 10 minutes, but generally it takes about 15 minutes to do one of these problems completely. So one problem down, one to go. We are going to read through the problem. Lots of information in that problem. From all of this information, oh no, this won't let me erase everything. Well, this ought to be interesting. All right. From this problem, we're going to figure out what our objective function is, write out our constraints. Once we have our constraints, graph the solution, feasible solution region for those constraints, find the corner points, plug the corner points into the objective function, and then answer the problem. So those are all of our steps. In exercise 2, it says, because of a new federal regulation on pollution, a chemical company has introduced into its plant a new, more expensive process to supplement or replace an older process in the production of a particular chemical. The older process discharges 25 grams of carbon dioxide and 50 grams of particulate matter into the atmosphere for each liter of the chemical that's produced. The new process discharges 15 grams of carbon dioxide and 40 grams of particulate into the atmosphere per liter produced. So basically, this company is making some kind of chemical. When you make chemicals, it releases toxins into the atmosphere, and that's bad for the environment. So the government has regulations on how much you can pollute the world. This is saying that this company has a new method that they can use that'll minimize the amount of pollution that they have. If you look at it with the newer method or the newer process, instead of discharging 25 grams of carbon dioxide like the older process did, it only discharges 15 grams. And it only has 40 grams of particulate matter compared to 50 grams of particulate matter from before. So the idea is this new process lets off less pollution, okay? So that sounds good, right? Great for the environment. The problem is, it was a key word here, it's more expensive. So from the company's perspective, it's gonna cost them more. And I'm not gonna say companies are unethical, but the company's bottom line is to make money. So yes, the other process is better for the environment, but the new or the old process is cheaper. So they basically want to find some kind of happy medium. How can we lower the amount of pollution that we're having, but also minimize our cost or maximize our profit in this case? Okay, let's finish reading the problem. We are here. The company makes a profit of 40 cents per liter and 15 cents per liter on the old and new processes, respectively. If the government allows the plant to discharge no more than, those are keywords here, no more than 12,525 grams of carbon dioxide and no more than 20,000 grams of particulate matter into the atmosphere each day. Finally, the question, how many liters of chemical should be produced daily by each process to maximize the daily profit? And what is the maximum daily profit? So our unknowns here are the number of liters produced by each process. So we'll have the old process versus the new process. So first thing, identify and label your unknowns. Let X represent the number of liters produced by the old process. And we'll let Y be the number of liters produced by the new process. The idea is the company wants to use a combination of the two to try to maximize their profit and also meet the regulations, government regulations for the amount of pollution that they can let off, okay? And then our objective function here is what? We are asked to maximize the profit. We want to maximize P equals, where are we given information about the profit? Somewhere in here. The company makes a profit of 40 cents per liter and 15 cents per liter for the old and new process. So it's 40 cents for the old and 15 cents for the new. Obviously, they make more profit on the old process. Okay, so I'm going to write this in terms of dollars. So for 40 cents, I'm going to write 0.40 times X. And then for 15 cents, 0.15 times Y. All right, so every time I recommend reading the whole problem, go down to the question. The question is where you can figure out what your unknown should be. What are we looking for? How many liters of each chemical we should produce by each process? Boom. What are we trying to maximize or minimize? We're trying to maximize the profit. Boom. That's our objective function. Any questions so far? All right, then from here, oh wait, I have stuff down here that I need to still erase. All right, don't pay attention to that graph. We won't be using that. From here, we want to come down and list out our constraints. So what do we have constraints on? We have constraints on the amount of pollution that we can have. The carbon dioxide and the particulate matter. Oh, I used red already. What color can I, oh, green. Okay. So let's start with the carbon dioxide. The older process has 25 grams of carbon dioxide for each liter, and the new process discharges 15 grams of carbon dioxide for each liter. And then how much carbon dioxide are we legally allowed to discharge? No more than 12,525 grams of carbon dioxide. How do we put all of this information together to write out an inequality? Well, we'll have 25 times however many liters we produced by the old process. That would be X. And then plus 15 times the number of liters we produced by the new process, that's Y. And then it says that it can be no more than 12,525. That means we can discharge less than that. That's great for the environment if you discharge less pollution. But the most that you can discharge is 12,525. That means 25X plus 15Y has to be less than or equal to 12,525 grams. So no more than gives us the inequality of less than or equal to. In the last problem, we had at least that gave us a greater than or equal to symbol. All right, next part, particulate matter. For the older process, we have 50 grams of particulate matter. And for the new process, 40 grams of particulate matter. And we are allowed to have no more than 20,000 grams. So putting that together, we have 50X plus 40Y. That should be less than or equal to 20,000. And then, of course, it's not explicitly stated here, but since X and Y represent the number of liters that we're producing of this chemical, X and Y both have to be greater than 0 or equal to. They can be equal to 0. All right. Remember, this is half of the battle. And for your homework problems tonight and for the next couple of sections and even for your lab that we're going to do in just a second, the first half of the problem is just taking this information in the word problem and being able to organize your data and set it up so that you know your objective function and you know your constraints. All right, and I'm going to switch over to the whiteboard so that we can graph this problem and finish everything up. All right, so to rewrite what we have, our profit function P was 40x plus, or 0.4x plus 0.15y. And then our constraints were 25x plus 50y. That's wrong. 15y is less than or equal to 12,525. And the other one was 50x plus 40y is less than or equal to 20,000. Okay, from here, what do? We want to look at the two lines. 25x plus 15y equals 12,525, and 50x plus 40y equals 20,000. Find the x and y intercepts. Once we find the x and y intercepts, graph the line, pick a test point, find our feasible solution region, find the corner points, plug them in. All right, let's go. So for the first equation here, we get 25x plus 15 times 0 equals 12,525 for the x intercept. So 25x equals 12,525. Let's divide. 12,525 divided by 25. X is 501. So our x-intercept is 501, 0. For the y-intercept, we'd end up with 25 times 0 plus 15 times 0 equals 12,525. Oops, I have a typo there, not times 0. That's 15 times y. Then 15y equals 12,525. And if we divide 12,525 by 15, we get 835. So 0,835. Big numbers here, but that's okay. For our next function, or equation, I should say, sorry. For the x-intercept, 50x plus 40 times 0 equals 20,000. So 50x equals 20,000, and x is equal to 20,000 divided by 50 would be 400. 400, 0. And last one, 50 times 0 plus 40 times y equals 20,000. 40y equals 20,000. Y equals 20,000 divided by 40 would be 500. So 0,500. All right. Now, what are we going to do with this information? We're going to take these points, plot the points, connect the points to draw our lines, and then find our corner points in feasible solution region. All right, on to the next page. We'll call this X and Y. Our X and Y intercepts that we ended up with here are a lot bigger than the ones that we've been dealing with before. We have 501 and 835. I don't expect you to make little tick marks, like 500 of them, where each tick mark represents one unit. You want to think about what scale would be reasonable. You can go by 50s or by 25s or by hundreds if you want. I'll go by, we have to go to 800s. I'll go by 50s. So 50, 100, 150, 200, 250, 300, 350, 400, 5, 6, 7, 8, 9, 1,000. All right. Okay, might as well put 900 in there. I don't know why I skipped it. 900. And then on the x-axis, we'll do the same thing. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right, you do not have to write down every single line like I'm doing, but you should write enough so that I understand what the scale is. All right, from here, I've forgotten what our points are. For our red line, we have 501, 0 and 0, 835. 501, 0 would be basically here, and then 0, 835. Oh, my lines got a little uneven up here somewhere, but 835 would be about here. And then we want to connect these two. Oh, I missed. All right, not too bad. For our second to, or for our blue line, our x-intercept was 400, 0, y-intercept 0, 500. All right. So this is interesting. These are our two lines. They don't even intersect. Is that possible? Is this right? We haven't done anything wrong so far. Everything is correct. These two lines just don't intersect. Let's pick a test point. We'll use 0, 0 for our test point. And we want to plug them into our original inequalities, which were 25 times 0 plus 15 times 0. That should be less than or equal to 12,525. Is this true? Yeah, that is true. And the other one was 50 times 0 plus 40 times 0 should be less than or equal to 20,000. Is this true when we plug in 0, 0? Yes, 0 is less than or equal to 20,000. So what does this mean? Our test point 0, 0 worked. We want to shade in everything that's on the same side as 0, 0. So that would be everything that's under both of these lines. All right. So everything under the red line, but also everything under the blue line. Here, since they don't intersect, the only region that would work is everything that's under the blue line here, because everything that's under the blue line is also under the red line. It works out. So we get this little triangle at the bottom. And this one's nice because all of our corner points are on the axes, so it's easy to find them. We don't have a lot more work to do. Our corner points here are 0, 0, 500, 0. Oh, no, I'm sorry, 400. Oops. 400, 0, and then 0, 501. All right, and then remember, you find your objective function in the beginning, and then you don't really use it again until the very end. So once you find your corner points, then we also want to plug these into the objective function, which is p equals 0.40x plus 0.15y. If we plug in 0, 0, the profit is 0. That one's pretty easy. If we plug in 400, 0, we would have 0.40 times 400 plus 0.15 times 0. That would give us 0.4 times 400 is 160. And then let me just move this down a little bit. This gives us a profit of 0.40 times 0 plus 0.15 times 501, which is 0.15 times 501. Did I do this right? 7515. I'm sorry. I wrote the wrong thing down here. I just realized. That's not 501, that's 500. I'm using the wrong point. These are both of the points for the second function. So that should just be 500 for our corner point. 500 here, and then this would be 75. All right, so our goal was to maximize this profit. Which number gave us the maximum profit? The point 400, 0. So what is this telling us? 400 represents the number of liters of the chemical that were produced by the old process. So we'll say when 400 liters are produced by the old process and none are produced by the new process, we have a profit of $160, and it's the maximum. So when 400 produced by the old process and 0 by the new process, we get a maximum profit of $160. So 160 is the maximum profit, and 40, 0 tells us the number of units we need to liters produced by each method to maximize. So basically this is saying, even though there's a new process that will produce less pollution, it will be better for the company to just produce fewer liters of the chemical and just stick to their old process instead of trying to make some with the new process and some with the old process. All right, one more we need to look at, our lab for today. So you can open up lab 4.2, day 2. It's just one problem. And it's one problem just like the ones that we've been doing, but it's broken down into parts for us. In this problem, it says, a furniture company manufactures 2 products, rockers and bookshelves. The profit is $30 per rocker and $42 per bookshelf. Next week's production will be constrained by 2 limited resources, labor and wood. The labor available next week is at most 900 hours, and the amount of wood is 2,400 board feet. Each rocker requires 4 hours of labor and 8 feet of board wood. Each bookshelf requires 3 hours of labor and 12 feet of board wood. And then the most important part. What's the question after all of this stuff? Find how many rockers and bookshelf units should be produced to maximize the profit. So the first thing we're asked to do here is, we have some variables. Define each variable as a complete sentence. We'll say, we want to know how many rockers and bookshelf units should be sold. So there's 2 different things. We should have 2 unknowns. Let X be the number of rockers, and let Y be the number of bookshelves. Okay, so what are you trying to find? How many unknowns do you have? Assign a variable to each of those unknowns. And then the next thing we're asked to find is our objective function. We're told here that we want to maximize the profit. Okay, and then we want to write out an actual profit function. Somewhere in here, we're given information about the profit. It's actually in the beginning. It says, if the profit is $30 per rocker and $42 per bookshelf, that would be P equals 30. And then we're told what our constraints are. It says we are constrained by 2 limited resources, labor and wood. So you should have an inequality for each of your constraints. I'll show the work for this kind of like 2 ways. Some people might be able to easily read through this paragraph and find your answers by like underlining like I've been doing. Some of you may find it more helpful to make a table to kind of organize your data. So let's do that. I always start with our unknowns at the top. We have rockers and we have bookshelves. Okay. And then our resource or constraints are labor and wood. What are we told about the rockers? Somewhere it's here. Oh, each rocker requires 4 unit hours of 4 labor hours, I'm sorry, and 8 board feet of wood. I was having trouble with that. So 4 labor hours and 8 board feet of wood. And then we're told each bookshelf requires 3 labor hours and 12 feet of wood. Okay, and I'm gonna highlight all of that here too. So we had 3 labor hours for one and 4 labor hours for the other. And we're also told that we have a maximum of at most 900 labor hours. So we'll have to take that into consideration. And then highlighting the others, we have at most 2,400 feet of wood. We need 8 and 12. All right, now that all of this information is given to us, our keyword here is we have at most 900 hours and we have a certain amount of wood. That means that is the maximum amount that we can use. You can't go over that. So we can have less than that if it helps, but we can't have more than that. When we see at most, we should have a less than or equal to sign. And I'll stop here after the setup and let you finish the rest. So our constraints would be for the labor, 4x plus 3y should be less than or equal to 900. We don't have more than 900 hours of work time available. And then for the wood, 8x plus 12y, that should be less than or equal to 2,400. We only have 2,400 board feet of wood to make these 2 items. So we can't use more than that. We can use less than that though. And of course, we always know that in these problems, X and Y have to be greater than 0 because we can't make a negative number of rockers and bookshelves. All right, so I'll stop here. What you guys should do for the rest of this lab is graph the 2 inequalities. And then once you find those, evaluate the objective function at the corner points. That's just plugging the corner points into the objective function. And then from there, you'll be able to find your maximum. Okay, so I'll stop here.